Okay, question one from 2019 on the higher paper, hardest question by student data. Question 22, are red and G green counters in a bag? A counter is taken at random. The probability that the counter is green is 3 out of 7. The counter is put back in the bag. 2 more red and 3 more green are put into the bag. So we have a total of 5 more counters added into the bag. The counter is then taken at random again. The probability that this counter is green is 6 out of 13. Find the number of red and the number of green that were originally in the bag. So now the mark scheme goes on to talk about getting an equation for the first situation before the extra counters were added, and an equation for the second situation where after the 2 red and 3 green were added, and you solve those equations, those simultaneous equations, because you have one from scenario 1, one from scenario 2. Combine those, you would get a value for R and G. So that's all well and good and takes a bit of time, but it's very, very achievable. So you'd either do that by substitution, which is what I did, or by elimination. Either way will get you an answer. But I came up with a much more simple way of figuring out the number of red and green counters. So let me take you through that. So we have the probability of picking green on that first pick is 3 out of 7. So therefore we can assume that because there's only 2 colours, the probability of picking red on that first pick was 4 out of 7, because those two probabilities have to add up to 1. So if we realise that we are out of 7, then we know that the total before extra counters were added, R plus G, is going to be a multiple of 7. Okay, because it's 3 out of 7 and 4 out of 7. So there could be 7 counters, could be 14, could be 21, etc., etc. We don't know. So in scenario 2, we then have 5 extra counters added. So we know that R plus G, the original total, plus 5 extra counters, well, that gives us a probability of green of being 6 out of 13. So we know that the R plus G plus 5 total must be a multiple of 13. So I thought I would start listing multiples of 7 to see. This would obviously match the first scenario. So 7, 14, 21, 28, 35. Might need to go higher. Don't know. Let's see. And then I thought I would add the 5 to those values because I want a multiple of 13 here. I'm looking for a multiple of 13, but it must first of all be 5 more than a multiple of 7. So 5 more than 7 gives me 12. Is that a multiple of 13? No. 5 more than 14 gives me 19. Is that a multiple of 13? No. 5 more than 21 is 26. Now that is a multiple of 13 because it's double 13. So I thought there must be 21. There must have been 21 in the 21 counters in total originally, and then when the 5 extra counters were added, we then had 26 because that would allow us to match up with the probabilities here and here. So if I want the number of green originally, I need 21 in total. So I need 3/7 of, which is multiply, 21. Well, 3/7 of 21. 21 divided by 7 is 3. 3 times 3 is 9. So I think there are 9 green originally. And the number of red originally would be 4/7 of 21. 21 divided by 7 is 3. 3 times 4 is 12. Sorry, this is red. Beg your pardon. So that'll be red. So 9 green originally and 12 red. Just double checking. 9 plus 12 is 21, and if I add 2 extra green there, 2 extra red, I then get 14. If I add 3 more green, I get 12, and 12 plus 14 is indeed 26. So that's just a last little check there. So we have 9 green and 12 red originally.